So, well, today we start a new group of lectures organized by CMSA and Tsinghua University together. And there will be 10 more lectures in the next few days, and including in January. And we invite Won Jones to give a talk about a couple of months ago. And well, of course, we were very sad to find out that he actually passed away a couple of weeks ago. And we so set up a few lectures in memorial of Won. So Cliff will be the chair for this talk for Edward Witten. So let's start. Cliff.
Yes, thank you. I'm going to introduce the speaker, Edward Witten. I imagine that anyone who hasn't been living on Mars or socially isolating for the past 50 years knows who Ed Witten is. I was thinking last night about, what to say, and thinking back on the history of gauge theory, it occurred to me that behind every advance in gauge theory is a foundational paper of Edward Witten. I mean, essentially from the very beginning, starting with the first solutions on R4 for the self-dual Yang-Mills equations, and then his influence with Atiyah, Bott, and Singer, his Floor-based his homology theory on the supersymmetric quantum mechanics paper of Ed Witten, and then of course Seiberg-Witten equations, Kapustin-Witten equations, Vafa-Witten equations, Gromov-Witten invariants, and then the whole topological quantum field theory story, quantum Chern-Simons theory, quantum knots theory, all of these things. The profound influence of Edward Witten. So anyway, so having said that, I'm very happy to have been asked to introduce him, and his title is Not Invariants from Gauge Theory in 3, 4, and 5 dimensions.
Thank you very much, Cliff, and also Yal for the kind words. So as you're going to hear, the Jones polynomial of a knot is going to be a major ingredient in my lecture. So the Jones polynomial is quite an extraordinary discovery that von Jones made in the early 1980s, where he went from questions in von Neumann algebras to problems in, things related to integrable lattice models of statistical mechanics in 2 dimensions in quite an extraordinary way, and invented this new type of invariant of a knot, the Jones polynomial. As you'll hear later in the talk, I got interested in it a number of years later, actually largely through Michael Atiyah's influence. I'll mention a few of the other developments during the talk. And the Jones polynomial has been studied by both mathematicians and physicists from an extraordinary number of viewpoints for ever since it was invented, which was approximately 1983. So we're all very sorry that von Jones is not with us today. He actually did hear a previous version of the lecture I'm going to be giving today, because we and also Cliff visited in New Zealand last winter for a few weeks. So we got to enjoy mathematical discussions with Von, and also a little bit of an introduction to some of his favorite New Zealand hobbies. But it's quite sad that he isn't with us anymore. So I'll go on to this lecture where you'll hear a little bit about a physicist's point of view of the Jones polynomial and just a few of the things that came afterwards. There are way too many for one lecture. So I'll be explaining the relations between a sequence of theories in 2, 3, 4, and 5 dimensions. In 2 dimensions, we'll have what are called the conformal blocks of the WZW model. In 3 dimensions, there's the Jones polynomial and its relationship to Chern-Simons gauge theory. In 4 dimensions, there's Super Yang-Mills theory. And in 5 dimensions, we'll have a candidate for categorification of the Jones polynomial. Or in other words, a candidate for a refinement of the Jones polynomial That's called the Kovanov homology of a knot. So the Jones polynomial is a rather subtle invariant of a knot in R3, such as the one I've sketched here. And ever since his original work, constructions of it have generally been related to mathematical physics in a bewildering variety of ways. Jones himself gave several related constructions of the Jones polynomial. The one that I'll mention today involved the Jones representations of the braid group. A braid in a mathematical sense is a picture like this one. So this is meant to be a three-dimensional picture projected to the plane. Time is running vertically, and at a given time you have a two-dimensional plane with points in it, 4 points in the case I've drawn. As time goes on, the points move around. And to make a braid, they move around freely, not intersecting each other, and then returning to their starting points. So pictures like that, this one is a braid with 4 strands. Pictures like that form a group. They can be composed by gluing one braid on top of another. So if I have this braid and another similar braid, I would just literally put the second one on top of the first, glue the two pictures together, and the topological classes of such pictures, or homotopy classes of such pictures, then form a group. So Jones constructed some rather mysterious looking representations of the braid group. The representation matrices depended on a complex parameter Q, so I will call them R sub I of Q, where I labels the particular Jones representation. And for each I, the representation matrices also depend on Q. So the precise number of these representations depends on the number of strands considered. So for example, I think for 4 strands, there would be just 2 representations. One of Jones's original definitions was as follows. First of all, you can build a knot by gluing together the top and bottom ends of the braid. You just take the 4 guys at the top here and the 4 at the bottom here and glue them together, let's say pulling out of the page toward me and then gluing it back on the bottom. So you glue the top to the bottom without introducing any crossings or intersections. And that turns a braid into a knot, or in general, what's called a link. A knot is an embedding of a single circle in R3. A link is the case of possibly more than one disjoint circle. Now, gluing the top to the bottom is a little bit like taking a trace. So it perhaps suggests that it's natural to take the trace of the representation matrices of Jones's representations. So what Jones did was the following. Suppose that B is a braid, and let curly I of B be the matrix that represents this braid in the representation R sub I. So I've demoted the complex variable Q to a subscript here, and now we think of the main argument of the representation matrix as the choice of braid. It's an n by n matrix for some n that depends on the number of strands and also on the choice of the representation I. So one of essentially Jones's original definitions is that a certain linear combination of these traces is the Jones polynomial. So there are certain functions Ci of Q that you have to include, and a linear combination of traces with these coefficients is a representation, is an invariant of a knot. And that invariant is called the Jones polynomial of the knot. Now, everything about this formula is somewhat mysterious. First, the construction of the braid group representations of Jones was non-obvious. Secondly, the particular function Ci of Q that you have to use were obscure. And perhaps most important, because the same knot can be constructed as the trace of many different braids, it's not at all obvious why traces of braid group representations are a good approach in making knot invariants. So I first learned about all these things approximately 5 years after Jones's original work from Michael Atiyah, who predicted that the mysteries should be unraveled by interpreting the Jones polynomial in quantum field theory. There was a very important step taken by Japanese mathematicians Tsuchiya and Kanya. They showed that the Jones representations are the ones that arise when you decompose the correlation functions of a two-dimensional conformal field theory known as the WZW model into conformal blocks, a decomposition that was originally analyzed by Knizhnik and Zamolodchikov. Well, the WZW model is a two-dimensional conformal field theory that depends on the choice of certain data, a compact symmetry group G and a positive integer K. You can generalize to non-compact groups, but then the theory is much more complicated. For today, we consider a compact symmetry group G, and then the model depends also on a positive integer K. It turns out that in the relation to the Jones polynomial, G should be SU2, and K should be related to the variable Q used by Jones by this formula here. An integer K corresponds to Q being a particular primitive root of unity. The WZW model has what's called primary fields in various representations of G. To make contact with the Jones representation, we consider a primary field phi in the two-dimensional representation. And then we look at its genus zero correlation functions. So to define these, we take a Riemann surface of genus zero, a sphere, like I've drawn here, a two-sphere. Then we take some points on the two-sphere, which I've labeled as Z1, Z2, up to Z5 in this picture. And then in physics language, we insert the primary field phi at each of these points. And then the WZW model produces a function which physicists know as the expectation value of this product of operators. I've written the operator as phi of Z bar, where the notation is just meant to tell us that these functions are real analytic, but they're neither holomorphic nor anti-holomorphic. So they depend on both Z and Z bar, but locally you could think of them as depending independently on Z and Z bar, which is what real analyticity means. So, as I said, these functions are neither holomorphic nor anti-holomorphic, and they cannot be factored as the product of a holomorphic and anti-holomorphic function. But Knizhnik and Zamolodchikov had shown that there are finite sums of products of holomorphic and anti-holomorphic functions. So the correlation function is the sum over a finite set of alpha of a product of a holomorphic function times the anti-holomorphic function. These are multi-valued holomorphic functions. So locally, you can make this decomposition with a certain set of multi-valued functions, but these multi-valued functions have monodromies. So for each n, you can define a vector bundle Vn over the configuration space of n points with a basis given by the F alphas. These are automatically flat vector bundles with the F alpha understood as covariantly constant sections. And the monodromy of these multi-valued holomorphic functions are the monodromies of a flat vector bundle. So they're monodromies when the points move around, give representations of the braid group. A braid is the configuration space of n distinct points on the plane. So a flat bundle over the space of n distinct points on the plane, in this case, the flat bundle whose sections are the F alphas, is a representation of the braid group. The single valuedness of the correlation functions of the WZW model implies that these representations are unitary. The observation of Tsuchi and Kanya, to simplify it slightly, was that the representations you get this way are the Jones representations of the braid group. So that was very important for me because although Jones had used mathematical physics from the beginning, the mathematical physics he used was much more distant from quantum field theory. And this was an interpretation of the Jones representations, although not the Jones polynomial of a knot, directly in terms of quantum field theory. Now, as understood by physicists at the time, the WZW model is a purely two-dimensional quantum field theory with no particular connection to three dimensions. But the relation of the conformal blocks of the WZW model to the Jones representations of the braid group showed that the WZW model somehow is connected to three dimensions because Jones had related his representations to knot invariants. And knot invariance means topological invariance in 3 dimensions. In this case, a topological invariance of a loop embedded in R3. Now, there were more clues in this period about relations of the WCW model to 3 dimensions, but there won't really be time to explain all of them. The most direct clue was in work of Eric Verlinde, who defined certain operators acting on the space of conformal blocks. And his work also led to important work on the conformal blocks by Moore and Seiberg. So a lot was going on in this period involving the ingredients I'm telling you about. But I won't give a detailed explanation of everything from that time. Now, if you want to relate the WCW model to 3 dimensions, there actually is a quantum field theory that depends on precisely the same data as the 2-dimensional WCW model. The data being a gauge group G, which for simplicity is a compact group, although it doesn't absolutely have to be compact, and a non-zero integer K. We simply do Yang-Mills theory in 3 space-time dimensions with gauge group G, but we choose the action to be not the usual Yang-Mills action, but the Chern-Simons function. So I've written the Chern-Simons function of a gauge group well, in detail in terms of a connection form with components A sub I. There are more abstract ways to write it down. As I've written it, it's not that obvious that this function has any gauge invariance properties because I haven't expressed it. It can't be expressed in terms of the Yang-Mills curvature F. In fact, it's invariant under gauge transformations that are homotopic to the identity. But in 3 dimensions, because pi 3, I can write but only semi-legibly. In 3 dimensions, and we run into a non-trivial homotopy group of the gauge group G, pi 3 of any simple E group is Z. So it's possible to have a gauge transformation that's not homotopic to the identity. And it turns out that this function isn't invariant. It's invariant under gauge transformations, homotopic to the identity, but not under others. I hope I can clear what I've done. Yeah. So it turns out that this function I is gauge invariant mod 2 pi k times integers, but it's not completely gauge invariant. In quantum theory, the action must be gauge invariant mod 2 pi times integers. Because the argument of the Feynman path integral, someone isn't muted, I think. The argument of the Feynman path integral is the exponential of I times the action. So to make this single valued, the action has to be well-defined mod 2 pi times an integer. That's why k has to be an integer, which is an argument originally due to Deser, Jakiv, and Templeton. And it's somewhat similar to the argument showing that in the WCW model in 2 dimensions, k has to be an integer. So that's part of the relation between the 2 models. Now, the importance here of using the Chern-Simons function rather than a standard Yang-Mills action is that it can be defined on an oriented 3-manifold W with no choice of metric tensor. We simply didn't use a metric tensor in defining the action. We used an orientation so that we could integrate a 3 form, but that's all the only property of W that we used. So therefore, the Feynman path integral of this theory doesn't depend on anything except W itself. In other words, if it can make sense at all, it will give a topological invariant of W. That's oversimplified because there's what's called a framing anomaly. So actually, you have to consider W as a framed 3-manifold. But at the general level of today's lecture, we won't go into such details. Now we can include a knot or an embedded circle K in W by introducing what is known in quantum field theory as the Wilson loop operator. The Wilson loop operator is simply the holonomy of the connection A around the knot K, which physicists write this way, and then you take the trace of the holonomy in some representation R. So the Wilson loop operator depends on an oriented knot K, so that you know in which direction to go around when you compute the holonomy, and the representation R. So now we can consider the Feynman integral with an extra factor of this holonomy operator. So now it depends on W and on the knot K and the representation. And it also depends on the integer little k in the action, but nothing else. So if, for example, W is R3, this will potentially give an invariant of a knot in R3. Now I'm going to state the basic relation between the 3D Chern-Simons theory and the 2D WZW model. If you want to study this theory with this action as a quantum field theory, one of the most basic things you're going to want to understand is what is the space of physical states. What that means is that you take some spatial manifold times time to make a 3 manifold, you quantize the theory, and you want to get a space of physical states of the system on that 2-dimensional manifold. So to quantize any field theory, you first construct the phase space, which is the space of classical solutions. It will be a symplectic manifold, and you quantize it. In this case, you find that if you quantize the Chern-Simons theory, you learn that the space of physical states of the 3D theory on some Riemann surface is the same as the space of conformal blocks of the 2D theory on the same Riemann surface. So for example, as I said, let's quantize the 3-dimensional theory on a Riemann surface sigma of genus G times R, where you could think of R as parameterizing the time. To construct the Hilbert space H sigma, you have to quantize the appropriate classical phase space. The classical phase space in general is the space of classical solutions of the theory on sigma times R. But the Chern-Simons theory has the property that the classical field equation is just F equals 0. In other words, a critical point of the Chern-Simons function is the same as a flat connection. The classical field equation asserts the vanishing of the curvature F equals dA plus A wedge A. So the classical phase space that has to be quantized is the moduli space of flat G bundles over sigma. This can be quantized by picking a complex structure on sigma, which then induces a Kähler structure on M sigma. In other words, the complex structure compatible with its symplectic structure, a complex structure where the symplectic structure is positive, a type 1,1 and positive. And then in such a Kähler structure, you can quantize by looking at holomorphic sections. The pre-quantum line bundle in the quantization is the kth power of what I'll call L. L is the fundamental holomorphic line bundle over M sigma, which in the case of a unitary group is called the determinant line bundle. And the physical Hilbert space is the space of holomorphic sections of the kth power of L over the moduli space of flat or holomorphic bundles. I've drastically shortened what actually is a long story, but the point is that the answer coincides with a known and, for some people, rather standard, although also rather abstract, description of the space of conformal blocks on a genus G surface. So lots of people studied the WZW model and its conformal blocks without being familiar with this description of them. But in other lines of work, it's actually a standard description. For example, for people who work on geometric Langlands. I probably learned this description from Graham Siegel. So as I said, this description may not be familiar to everyone, even if you're familiar with the WZW model, but it's widely used in some areas. So the fact that the physical Hilbert space of the 3-dimensional theory is the space of conformal blocks in 2 dimensions is at least one way to say the basic link between 2 and 3 dimensions. Well, to get the Jones representation of the braid group, we simply take sigma to be R2 or CP1 in a slightly different approach, but with parallel Wilson lines. In other words, we take Wilson lines. Remember, a Wilson line is simply a knot on which we're considering the holonomy of the connection. But, well, a knot is an embedded 1 manifold. Here I take the embedded 1 manifolds to be, in the first approximation, just straight lines that run vertically in the time direction. We quantize in the presence of these Wilson lines and we get a Hilbert space. But, well, the theory of the, well, a more thorough study of this quantization shows that as the points move around, we get a natural flat connection, which is the same as the flat connection I described in the context of the WZW model. And so a better way to say it is that when we quantize in the presence of these Wilson lines, we get not just a Hilbert space, we get a vector bundle. The points could have been anywhere. So the Hilbert space is really the fiber of a vector bundle over the space of points. And as the points move around, what we get really are the Jones representations of the braid group by quantizing in the presence of these Wilson lines. Then some further arguments, you can obtain a formula for the expectation value of a general Wilson operator in R3 that coincides precisely with Jones's formula for the Jones representations, the Jones polynomial, in terms of traces. Maybe this is a good moment to stop and ask if there are any questions. So,
I don't see, yeah,
is there a question?
I don't see any, so go ahead.
Okay. Now, in this presentation, since k had to be an integer, the theory is really only defined for integer k, or in other words, it's only defined for q of this form. That's a formula originally due to Tsuchiya and Kanya. They weren't studying the WZW model, but only the conformal box. So in their work, k didn't actually have to be an integer, and they had this general formula.
Ed, can I ask a question? There's
Please.
a question. The question is the coefficients of C.
Yes.
What's any interpretation in the context of the two-dimensional and three-dimensional?
They have a neutral, yeah. Okay, I unfortunately didn't plan on explaining that, but C are related to the following. You can consider a basic link in 3 dimensions where you have two unknowns, but they're linked together. And you could consider the expectation value of that product in 3 dimensions. So C can be expressed in terms of that. There's well, at least in I think there are many ways to get these formulas, but my original approach involved a little bit of surgery to relate a knot in R3 to a braid. I embedded the braid in S2 times a circle. And then I did a surgery relating S2 times a circle to R3. That turned the braid into a knot. And to do the surgery, you needed to do a little calculation involving what would have happened with the simplest kind of link. And that calculation leads to these coefficients. So that was their interpretation. There are a number of other interpretations of these functions. Okay, it takes, to really properly explain that, it takes an argument that I'm not, or at least I wasn't planning to give today, to explain exactly how you can go from braid group, why you can go from braid group representations to a knot invariant.
Thank you.
Okay. I'll just recapitulate it slightly as follows. So a knot lives naturally in R3, but in quantum field theory, to get a trace usually means you have a circle times something. So you should have a circle times either S2 or R2. And then the braid is a bunch of points in R2 or S2 that's propagating around the circle. So that setup leads naturally to braid group traces. But if you want a knot invariant, you should be in R3 rather than in R2 times a circle or S2 times a circle. So you have to investigate a surgery that compares S2 times a circle to S3 or R3. And when you do that surgery, you end up with this formula. So I didn't plan to go into that degree of detail today because I wanted to go on to 4 or 5 dimensions. So in this presentation, the theory is only defined for an integer k, or in other words, only for particular roots of unity. Now, if you want a theory that's defined on an arbitrary 3 manifold W, that is believed to be the right answer. In other words, the Jones polynomial of a knot in R3 turns out to have an analog for an arbitrary 3 manifold W with or without a link. But this general analog is believed is defined only for roots of unity. So as a physicist, you'd say it's naturally defined for these roots of unity, but but algebraically can be defined for any root of unity. However, if you consider just knots in R3, one can, then what you get this way from the quantum field theory can be analytically continued from integer values k to complex values of k, and thus the knot invariant is a function of a complex variable q. And of course, that's the way Jones originally just presented it. More specifically, j of q is not just a random holomorphic function, it's a Laurent polynomial in q, which is why the invariants that Jones discovered are described as a knot polynomial. Now, that's mysterious from the point of view of the three-dimensional gauge theory, but the interpretation in other approaches makes it more clear. So that was actually true in all of Jones's original approaches, but for example, in terms of two-dimensional conformal blocks, it follows from rather simple properties of the construction by Knizhnik and Zamolodchikov that J is going to be a Laurent polynomial in Q. So the three-dimensional approach made three-dimensional topological invariants more obvious, but did not give a direct explanation of why the invariants are a polynomial. Instead, one only got invariants defined at integers. So for about 20 years, I accepted this state of affairs, that there were formulations of the Jones polynomial that explained directly why it was a polynomial, but didn't make three-dimensional invariants obvious. And there was the Chern-Simons theory that made three-dimensional invariants obvious, but didn't explain why it's a polynomial. It was a little bit frustrating, but I couldn't do anything about it. So I went on and thought about other things. But by about 20 years later, new developments, mostly involving what's called the volume conjecture, motivated me to look for a new explanation of why the 3D Chern-Simons path integral for knots in R3 can be continued away from integer k. So the volume conjecture is usually formulated as a statement that if you consider a representation of SU2 of dimension, I think it's k plus 1, and you take k to infinity, then in the limit you get the exponential of the hyperbolic volume of a 3 manifold, assuming you're on a, well, I've left out a few details about what the limit is supposed to be. But if you formulate it, if you look carefully, you'll see that some analytic continuation is involved relative to what's natural physically. Anyway, the volume conjecture was a fascinating statement. Without going into too much detail, it relates the Jones polynomial and its analog for a 3 manifold to the hyperbolic volume, the volume of a hyperbolic 3 manifold. So I was interested in knowing why it was true, and I realized that to express it in terms of physics really fundamentally involves something I didn't know, because it involves an analytic continuation away from integer k. You can almost, but not quite, formulate the volume conjecture in terms of what happens at integer values of k. So understanding this turned out to involve a link between 3 and 4 dimensions that I think is just as interesting as the link between 2 and 3 dimensions, though it's not yet nearly as well known, I don't think. So before I'm going to explain the story about analytic continuation of the Chern-Simons path integral, let's just briefly discuss analytic continuation of an ordinary integral. So here's an integral in 1 dimension, and it depends on a parameter a. And I've called the integral z of a. Now, to improve the analogy between this integral and a Feynman integral, I'm going to derive a simple identity which will be the analog for this integral of what physicists call a Ward identity in quantum field theory. So the integral, by integration by parts, we learned that the integral of d by dx of x times this expression is 0. And that can be converted into showing that z of a obeys a differential equation. So when we generalize the path integral, we want to preserve the Ward identity, which in this case means that we want to preserve the differential equation. So if you want to know in mathematical terms what the word identity means, there's a mathematical theory of what people call skein modules. If you're familiar with that, a skein module is a set of invariants of knots that obey relations that are what I'm here calling the word identities. Now, to generalize the original integral, we analytically continue from x to a complex variable z. And then we can write the original integral, as I've done here, where gamma is an integration cycle that happens to be the real axis. So we're going to generalize the integral by considering some other gamma by integrating the same differential form over some other integration cycle. Well, what sort of integration cycle can we use? A closed cycle is no use because the integral will vanish by Cauchy's theorem. In other words, if we just integrate over a closed orbit in the plane, oh, sorry. I was trying to, oh, sorry. Okay, well, I'll try to keep talking while I try to find the screen that I wanted to share. If we integrate over a closed cycle in the plane, then we're going to get 0 by Cauchy's theorem. Huh? Why didn't that work? This will work. So we need to pick an integration cycle with the property that the integral converges. What are you seeing now, if I could ask? You're not seeing the correct page, are you?
We're seeing your desktop and it's all of your files. So,
all right, let me, I don't know why you're seeing my desktop, but I can just put the right file on the desktop.
if you just open whatever you want to show and full screen it.
Okay, all right. Okay, I'm not going to try to annotate it. A closed cycle is no use because the integral, we're integrating the exponential of a holomorphic function. So the integral over a closed cycle will vanish by Cauchy's theorem. We can't let the integration cycle have a boundary because then the word identity, its proof involves integration by parts, so it will fail. So the only option is for a cycle that runs from infinity to infinity in such a way that the integral converges. So for example, here are two possible integration cycles. We could start it and end on the positive or negative x or y axis. So I've presented this in one dimension, but it should be clear that we can treat an n-dimensional integral in much the same way. We first analytically continue from real variables xk to complex variables zk, and then we consider an integral over a suitable cycle in Cn. The properties we want for the cycle are the following. It's got to be middle dimensional and without boundary. And the function minus the real part of f has to go to minus infinity at infinity along gamma so that the integral will converge. For every such gamma, we'll get a generalization of the original integral, and any differential equations you can prove by integration by parts will be satisfied. It turns out that there's a nice theory of the possible gammas given by Morse theory, and this also gives a good framework for understanding analytic continuation of such integrals. So what we wanted to do today is to place the Chern-Simons path integral in the same framework. A quantum mechanical path integral in 0 + 1 dimensions can be studied very similarly, but for today we'll just consider Chern-Simons theory. So the Chern-Simons path integral is an integral over an infinite dimensional space U of all gauge fields A for gauge group G. The integrand is the exponential of a polynomial, so we're in roughly the same situation as before. There's no problem formally to analytically continue the integrand. We replace A by a complex valued connection, curly A plus I phi, where phi is a one form valued in the gauge group. The gauge group is now the complexification of the original gauge group. For example, we replace SU2 by SL2C. Also, the exponent of the path integral is a polynomial in A, and we can analytically continue it to the same polynomial in curly A. And we replace U by space U sub C of complex valued connections. The only catch is that the integration has to run over a middle dimensional subspace of the space of complex valued connections. So we need to find a middle dimensional subspace. We need to find a subspace that's middle dimensional and has the property that the analytically continued path integral converges. So how are we going to do that? Well, there's a standard way to handle the first part, which is important in a lot of areas of math and implicitly physics, although not always made explicit in physics. In math, for example, it's used in fluorocohomology and lots of other things. So let U sub C be any set of fields on a manifold W, manifold dimension higher whose boundary is W. So schematically, the picture is like this one. Here's W, it's the boundary of X. Then you pick, roughly speaking, any elliptic differential equation on X, such that the desired fields on W can be interpreted as boundary values for a solution on X. And you define gamma to be the subspace of fields on W that are boundary values of global solutions on X. So this subspace will be within a finite dimensional amount of being middle dimensional, the difference being given by an index. For example, suppose W is a circle and UC is the space of complex valued scalar fields phi. Well, first let's pick a middle dimensional subspace by hand. We make a Fourier expansion of the function, and we define gamma by setting to 0 half of the Fourier components, say the ones where n is less than 0. But we can put this in our picture. We regard the circle as the boundary of unit disk in the complex z-plane, and we write z as r e I theta. So now, okay, here's our circle. It's the boundary of a disk X. And we regard the scalar field phi as the boundary values of a scalar field on X, which I'll also call phi. And the elliptic differential equation we pick is d bar phi equals 0. A general solution can be expanded in powers of z with non-negative coefficients. So when restricted to z equals 1, what we had before, with the negative Fourier coefficients vanishing. So in other words, the space of boundary values of solutions on X is the middle dimensional subspace that we defined by hand at the beginning. Now, if we go back to our problem with the complex valued connection curly A on a 3-manifold W, what we now do is we take W to be the boundary of a 4-manifold X, and on X we consider some differential equation, P of A phi equals 0. Now, if all we want is a middle dimensional subspace in the space of complex valued gauge fields, then we can use more or less any elliptic P. But P is essentially uniquely determined, or almost uniquely determined, if we want the path integral to converge. Just as in the one-dimensional example we started with, the path integral is in danger of diverging because after analytic continuation, the integrand of the path integral is no longer imaginary. In ordinary term science theory, the integrand is I times something real. Now it's I times something complex. So the exponent has a real part which is unbounded above, and therefore the integral is in danger of diverging. What will save the day as an identity if we could write the exponent of the path integral as the integral of p squared, something positive, plus something negative. Then that'll say that although the real part can be positive in general, it's negative when p equals 0. So such an identity says the dangerous left-hand side isn't negative in general, but it's negative when p equals 0, so it'll be negative on our integration cycle. Now, if you're familiar with supersymmetric Yang-Mills theory, then in looking at the last slide, you might notice something. the negative term on the right-hand side is part of the action of n equals 4 super Yang-Mills theory. You can think of the one form we introduced as 4 scalar fields of n equals 4 super Yang-Mills theory topologically twisted to turn them into a one form. The other 2 scalar fields have been set to 0 in this formulation. And the fermions of n equals 4 super Yang-Mills theory and also the other 2 scalar fields are part of a more complete description of a path integral that's a topological invariant. So related to the fact that the identity is linked in this way to n equals 4 super Yang-Mills theory is that the equations p equals 0 are supersymmetric equations for a twisted version of n equals 4 super Yang-Mills theory. In fact, Kapustin and I had run into these equations in our work on gauge theory applied to geometric Langlands. So we'll soon see why that's useful, but for the moment, let's leave aside the relation to super Yang-Mills theory. So the picture is as follows. We have a closed-oriented 3-manifold W. For any choice of a 4-manifold X whose boundary is W, we get an integration cycle for an analytically continued version of the Chern-Simons path integral on W. The integration cycle U consists of all complex gauge fields on W that are boundary values of a solution of the equation p equals 0 on X. Now, for an integration cycle of this kind, there's never any integrality condition. K does not have to be an integer. I think, well, I'm going to, okay. I'm going to explain that by a one-dimensional analog of what's going on. So instead of discussing Chern-Simons theory, I've written down a simple integral that depends on an integer k. So we integrate on the unit circle in the complex plane. This function, k is an integer, t is a complex parameter, and this integral defines a Bessel function. Now, if we don't want k to be an integer, we can simply change the integration cycle. We replace the integration cycle in the complex plane by the contour I've indicated that comes in from the negative real axis and goes back, comes in below the negative real axis and goes back above the negative real axis. As long as t has a positive real part, the integral in this cycle converges. And you can forget about k being an integer. Of course, you've lost something. When k was an integer, we had an entire function of t. On the original integration cycle, this function is manifestly an entire function of t. By changing the integration cycle, we can forget about k being an integer, but we lose something. We no longer have an entire function of t. T had to have a positive real part to make the integral in the new cycle converge. And we definitely change the analytic properties of the function, but we can get away from integer k. So that's something like what we've done in Chern-Simons theory. The original integral was analogous to the integral on the unit circle. K was an integer. The modified problem that uses the 4-manifold is like integrating on this other cycle, where k doesn't have to be an integer, but some properties are lost. So what we're doing to get away from integer k is an analog of this. And if you ask what's lost in going away in this way from integer k, the answer is that we had to choose the 4-manifold X, and that spoils topological invariance of W, because in general, there will be no way to pick an X such that all diffeomorphisms of W extend over X. So we have made some limited loss of topological invariance, reducing ourselves to those diffeomorphisms of W that extend over some chosen X. But in return for that loss, we've gained the fact that k doesn't have to be an integer. But there's an important case in which we don't lose anything, and that's the case of knots in R3. And that's basically because knots in R3 are canonically, well, R3 is canonically the boundary of a half space in R4. And that doesn't really lose any topological invariance. So Anyway, for the special case of knots in R3, you can argue using Morse theory that all integration cycles are equivalent. So the standard integration cycle can be replaced by one for which k has no reason to be an integer. So we get a new explanation of why the Jones polynomial, but not its cousins, the three manifold invariants, can be analytically continued away from integer k. However, because of the relation to Super-Yang-Mills theory, we actually get much more. The equation p equals 0 is an equation of supersymmetric localization for n equals 4 Super-Yang-Mills theory in 4 dimensions. In other words, the theory has a particular supercharge q, satisfying q squared equals 0, such that if you make a topological field theory by passing to the cohomology of q, the Feynman integral in 4 dimensions localizes on solutions of p equals 0. So this type of localization is a generalization of Doerster-Ekman-Atiyah-Bott localization in equivariant cohomology. It has a lot of applications in quantum field theory as well. So what I've said up to this point can be stated in a more physical way. Let X be a 4 manifold with boundary W. We can't preserve all the supersymmetry of n equals 4 Super-Yang-Mills theory when we formulate the theory on X, unless X is flat. But even if X isn't flat, we can pick particular couplings to preserve the supercharge Q. So we can assume that Q remains a symmetry on any X. And we also pick a particular boundary condition along W, which is a subtle and important part of the story. When this is done, the statement is that n equals 4 Super-Yang-Mills on X gives an analytically continued version of Chern-Simons theory on W. So the analytic continuation of the Chern-Simons path integral on W is just a particular gauge theory path integral on X. The boundary condition we need has a simple description in terms of branes of string theory. It arises from a D3 NS5 system with a non-zero theta angle. But it's actually a rather unusual boundary condition from a topological field theory point of view. It's not too unusual in the underlying n equals 4 Super-Yang-Mills theory. It's a first order boundary condition that's a standard elliptic boundary condition in the second order Yang-Mills equations. But in the theory localized on solutions of p equals 0, the boundary condition becomes trivial. It just says that p equals 0 along the boundary. So in the twisted topological field theory, this boundary condition looks very strange at first sight. It just tells us to integrate over the infinite dimensional space of all solutions on X of the equation p equals 0. This boundary condition has an analog in dimension 2, which was discovered by Kapustin and Orlov. Now, the step I've described in going from 3 to 4 dimensions is relatively non-standard. But once we make this step, we can get a lot farther using more standard arguments. First, we apply electric magnetic duality to the 4-dimensional n equals 4 theory. So in terms of branes, that does something simple. It changes D3 NS5 to D3 D5. In terms of gauge theory, what happens is the following. First, the gauge group G is replaced by the Langlands GNO dual group, G dual. For example, SU2 is replaced by SO3. But more interestingly, a symplectic group, SP2N, would be replaced by an orthogonal group, SO2N plus 1. The parameter Q of the Jones polynomial becomes e to the I theta, where theta is the gauge theory theta angle. That means that a field of instanton number n is going to be weighted by Q to the n. So the Jones polynomial, which was a Laurent polynomial in Q, is the expansion of the Jones polynomial as a Laurent polynomial in Q is going to turn into an expansion in contributions of different instanton number. In terms of the bulk localization equations, nothing happens. Localization is still in solutions of p equals 0. But because of the flip from NS5 to D5, the boundary condition is completely different. It now determines an elliptic boundary condition on the equation p equals 0, but an unusual elliptic boundary condition, as I'll explain shortly. Because the equation and boundary conditions are elliptic, it makes sense, or at least it will make sense if compactness issues, which actually have been aspects of which have been investigated in recent papers by Taubes, but which have not been fully settled. But modular compactness issues, you can hope it will make sense to count with signs the solutions of the equation p equals 0 that satisfy the boundary condition. And then if an is the number of solutions of p equals 0 with instanton number n that satisfy the boundary condition, supersymmetric localization will tell us that the partition function is the sum of an q to the n. And that will then be a dual formula for the Jones polynomial. In other words, the coefficient of q to the n in the Jones polynomial is supposed to be the number an of solutions with instanton number n that satisfy the boundary condition. And if you ask what happened to the knot, the answer is that the knot is still there in the boundary, and the boundary condition you have to use in this description is the rather subtle boundary condition that depends on the knot. So the knot is completely encoded in the boundary condition. So to get the Jones polynomial, the 3 manifold should be just R3, and X should be, the 4 manifold should be R3 times a half line. And we need a rather special boundary condition in the boundary. The boundary condition that we need has all the general properties of an elliptic boundary condition, meaning that with this boundary condition, for example, the operator, self-adjoint operator, well, P becomes a self-adjoint operator with a discrete spectrum if you're on a compact manifold, for example. But it's constructed in an unusual way by requiring the fields to have a certain sort of singularity along the boundary. So pick coordinates, local coordinates x along the boundary and a coordinate y normal to the boundary. So the boundary is at y equals 0. And write the one form phi as a tangential part plus a normal part. The boundary condition is that the tangential part should have a singularity that I call a nom-pole. It blows up as 1 over y when y approaches 0, where T are a standard set of generators of the Lie algebra of SU2. I call it a nom-pole because Nom introduced this kind of singularity. Nom studied a one-dimensional analog of these equations, or a one-dimensional reduction of these equations, which he used to construct monopole solutions in R3. And in his work, this kind of singularity at the endpoint was important. So that's why I call the singularity a nom-pole. So, well, this is the boundary condition away from a knot. And there's a refinement of this along a knot. Along the knot, you require a more complicated type of singularity that I won't describe today. So anyway, schematically at least, although I haven't fully defined the boundary condition, this is a dual formula of the Jones polynomial with a new interpretation, conjecturally, of the coefficients of the Jones polynomial as a Laurent series in Q. But there's one more step we can take. From this starting point, we can categorify the Jones polynomial and get a candidate for the Kovanov homology of a knot. What we get is closely related to work of Gukov, Schwartz, and Waffe, whose starting point was earlier work by Ugri and Waffe. There's also a variety of works with somewhat related perspectives. For example, a recent paper by Mina Aganagic from earlier this year. In terms of branes, categorification means replacing the D3, D5 system by a D4, D6 system. Starting with D3 branes on a 4-manifold X, the chain is that first you replace X by X times a circle, but then you decompactify the circle to the real line. So in other words, instead of considering a D3 brane on X, you can consider a D4 brane on X times a circle. And in topological field theory, that kind of does nothing. But then if you replace the circle by R, it does change the picture and you get categorification. So as I just said, introducing the circle does nothing, but replacing the circle by the non-compact real line corresponds to categorification. Categorification means you construct a physical Hilbert space, H, rather than purely numerical invariants. This Hilbert space is Z times Z graded by instanton number n, and also by fermion number F, which in this context is given by an Atiyah-Patodi-Singer eta invariant. To decategorify, you do by taking a supertrace or index, and that gives back the Jones polynomial. So categorification means, in this context, we construct a Z times Z graded Hilbert space H, where the Z times Z grading is by instanton number n, the instanton number of a gauge field on X is an integer n, and then there's a fermion number F, which is given by the Atiyah-Patodi-Singer eta invariant of a field that satisfies the equation P equals 0. And the Z times Z graded Hilbert space has the property that a certain trace in it reconstructs the Jones polynomial. The Jones polynomial is an Euler characteristic in this Hilbert space. Mathematically, without mentioning brains, what happens is the following. Remember, the Jones polynomial comes from counting solutions of an equation. In general, as far as I know, you can't categorify the space of the set of solutions of an equation. However, according to Morse theory, you can categorify the set of critical points of a function f. The categorification of the set of solutions of df equals 0 is the cohomology of M, the real Durham cohomology. So if we want to categorify the Jones polynomial, we want the set of solutions of the equation P equals 0 to be the critical points of some functional. That's actually not true in a generic form manifold. And if you just look at the equation P equals 0 at first sight, it won't look like it's true. If I hadn't known that the Jones polynomial had been categorified by Kovanov and other people, it never would have occurred to me to try to write the equation P equals 0 as the equation for the critical points of something. But if you know the Jones polynomial has been categorified, then you look for it. And you find out that if the form manifold X is W times a 1 manifold, where here we can just take W times a half line, then you actually can interpret the equation P equals 0 as the equations for the critical points of some gamma. So the equation is schematically delta gamma delta phi equals 0 for some energy function gamma that depends on all the fields, the full set of fields that occur in the equation P equals 0. But this is a gamma that you can only define for X of a particular kind, not for a general form manifold. Categorification means you add another dimension, replacing X by Y, which is X times R, where R is parameterized by a new time coordinate. And you study the gradient flow equation. d phi dt is minus the gradient of gamma. Now, in order for categorification to work in this context of field theory, the gradient flow equation has to be elliptic. Generically, if you take some local functional gamma of some fields, well, first you can always write down a gradient flow equation, but it normally is not elliptic. I only know a few cases where you get an elliptic equation that way, and this is one of them. Since it's elliptic, it makes sense to count its solutions, assuming the relevant compactness issues can be resolved. Assuming this, we can construct an analog of Fourier cohomology, and this would be the categorification of the Jones polynomial. Concretely, it means the following. The solutions of P equals 0 on a form manifold X are the classical vacua. We make a Hilbert space H0 with one basis vector for each classical vacuum. A classical solution has two integer invariants. One is the instanton number n, the other is the eta invariant, which in this context is an integer f. Because we have two integer invariants, we get a z times z grading of h naught. The physical Hilbert space, okay, h naught depends on the knot because the knot entered in boundary conditions on this equation P equals 0. However, the physical Hilbert space is not h naught, but rather it's the cohomology of a differential or supercharged Q that acts on h naught. The matrix elements of Q between different basis vectors in h naught are computed by counting gradient flow lines between different critical points, as usual in the supersymmetric approach to Morse theory. So finally, this is the conjectural picture for a gauge theory description of Kovanov homology of a knot in terms of counting solutions of differential equations in 5 dimensions. And what's needed to make it rigorous is primarily an understanding of compactness issues associated with solutions of those differential equations. So we've actually got on the line the expert on such questions here, namely Cliff. So you could consider asking Cliff questions after my talk. So in summary, we've discussed the relations between a chain of theories in dimensions 2, 3, 4, and 5. In dimension 2, we had the conformal box of the WCW model. In dimension 3 was the Jones polynomial and its description by Chern-Simons theory. In dimension 4, we relate this to n equals 4 super-Yang-Mills theory. And in the last step, we go to dimension 5, the categorification of the Jones polynomial. Or at least I assume that's the last step. I can't see any more steps to suggest. So as far as I know at the moment, that's the last step. Although some aspects of it can be well understood with a certain 6-dimensional conformal field theory. For gauge theory, as far as I know, 5 dimensions is the last step. Thank you. This is what I have to say today.
Well, thank you very much, Ed. That's really an amazing picture you've thrown together here.
Thank you.
So I guess we could take questions. I have a question here. Someone's asking, besides R3, are there any other 3 manifolds where the integer k can be analytically continued to a continuous variable?
Well, for any 3 manifold W, if you pick an X with the boundary W, you can make this analytic continuation. Not very much is known about what you get. In general, it will spoil some of the invariants of W because what it will preserve will be the subgroup of diffeomorphisms W that extend over X. So for example, if W is a 3 torus, what could you take X to be? X could be, take a circle in the 3 torus, it's the boundary of a disk. So a 3 torus is the boundary of a disk times a 2 torus. But to do that, you pick one of the circles in the 3 torus. So you broke some of the symmetry of the 3 torus. So you can do this, but you will typically lose some of the 3-dimensional symmetry. It's not very well understood what you'll get. But I might say that Gukov and co-authors, I'm not going to try to list them because I'd forget some, have in a different language and not emphasizing the gauge theory interpretation, but with a different approach to the same brain system, have investigated some of what you get for other 3 manifolds. But in general, I'd say that it's in its infancy. Not too much is known.
We have another question, which is what part of the chain of reasoning breaks if you attempt to categorify by passing to a D5, D7 system? This is from Arnav Tripathi.
Well, it's a miracle we got an analytic equation in 5 dimensions, I think. So I don't know any natural elliptic equations above 5 dimensions we should be trying to get. But, okay. The link to the Jones, but see, okay. I think the question is fine. So the Jones polynomial, we analytically continued putting D3 and S5. So that's why we had to, we were in 3 dimensions with the Jones polynomial. So there was an important 3. That's why we had to use D3 and S5. And then we were lucky that S duality converted S5 to D5. So we had a dual description by D3, D5. Then we can lift it to D4, D6. The question, I believe the question is, by lifting further to D5, D7, would we get something interesting? I'm not going to answer no to that question, but I'm also not going to tell you what we get that's interesting. I haven't been able to see how to get anything interesting by going to D5, D7, but I'm not going to say you can't get anything interesting. In 5 dimensions, Yeah, I think I better stop there. Okay, in 5 dimensions, you get this nice elliptic equation. If you try to go farther, you have to think of something new to do. That's why there's a question mark here. I can't suggest the next step, but I'm not going to say for sure there isn't one.
Thank you. So we have more questions. Arnav again, why did you lose topological invariance for your analytically continued general 3-manifold plus link invariance? Your argument for getting from 3D to 4D was to get from W to X, such that the boundary of X is W. It seems that you're allowing the possibility of X equals W cross R plus, and then at least for diffeomorphisms isotopic to the identity,
Yes.
if W is to extend.
Yes. Yeah. Okay. That's a good question, and it points at something I slightly hid in the lecture. So if we do W times R plus, since it's not compact, we'll need a flat connection. We'll need a boundary condition at infinity on R plus. And I'm hesitating because it's not completely obvious why we can't just pick the trivial flat connection as a boundary condition. So, okay. I'm hesitating. I'm not absolutely sure what will happen if you try to take the trivial flat connection. If you take a typical flat connection at infinity on R plus, of course, that again involved a choice, so it will break topological invariance on W. But I'm simply not sure what will happen if you try to take the trivial flat connection so as to preserve topological invariance. I think I should leave it at that. I might be forgetting something. Well, okay. It'll matter some, okay. It'll be better if the trivial flat connection is isolated, which it will be for a lot of 3-manifolds. So if you have a 3-manifold where the trivial flat connection is isolated, you can try to proceed with the trivial flat connection at infinity as a boundary condition. I don't want to make any promises about what's going to happen. There are an awful lot of things here, most of which haven't been investigated.
Another question from Andrew Nikish. Does your categorification of the Jones polynomial shed any light on the volume conjecture? A certain limit of the color Jones polynomial of the knot in a 3-sphere would give the volume of the knot complement.
Well, I didn't see that categorification helped with the volume conjecture. The volume conjecture, to be honest, I don't understand from a physical standpoint why the volume conjecture should be true. The volume conjecture was part of my motivation in figuring out how to analytically continue away from integer k, and relating, ultimately that turned into the relation from 3 to 4 dimensions. But I didn't learn in that work why the volume conjecture had to be true. All that happened was that I defined an integer invariant with the property that if that integer is non-zero for a given knot, then the volume conjecture is true for that knot. But I did not discover any reason that the integer in question is non-zero for every knot. So I don't even know how strong is the evidence for the volume conjecture. To me, if you study 100 hyperbolic knots, maybe you'd find one where the invariant is 0, and the volume conjecture would be false for that knot. But maybe the volume conjecture is true. If it's true, it's definitely true for a reason I didn't discover.
Are there other questions? Okay, well, here we have a question. Augustin Marino, I have 3 questions about low dimensions. 1, what is left of the extra fields from n=4 back in the original Chern-Simon theory? That's his first question.
They go away. So, okay, the extra fields make up a machinery. Well, if by extra fields you mean the fields that I didn't include in my lecture, two more scalar fields and a bunch of fermions. They go into a machinery that's needed to make the four-dimensional path integral a topological invariant. So you can apply localization to it. But when you do apply localization, they go away, and you're left with the analytic continued three-dimensional integral.
Second question, after taking electromagnetic duality, can you go back to 3 dimensions?
As far as I know, the answer to that is no. So, okay, you can do, well, so when you're in 4 dimensions, you have this twisted supersymmetric theory. You can try to localize it. Before electromagnetic duality, localization tells you it localizes on a 3-dimensional analytically continued path integral. But after electromagnetic duality, localization just tells you to count the solutions of p equals 0. And you don't get any advice on how to give a 3-dimensional interpretation of that. So as far as I know, the after duality picture, you're in 4 dimensions. You can go up to 5, but not down to 3, as far as I know.
Okay. And then the third question, can you analytically continue the relationship between Chern-Simons and WZW?
So an example of what that question would be concretely is, can we, so the Jones representations of the braid group, we see them in Chern-Simons theory at integer k, but Jones constructed them in terms of a complex variable k, or he called it q. So an example of the question would be, can we see the, can we do something with the 4-dimensional integral theory to see the continued representations of the braid group? It makes a lot of sense that you could, but it's not something I've really done. Yeah, I think it makes a lot of sense. What comes to my mind is that the braid group involves points on S2. And then you have R, which parameterizes how the braids move around. It has to be the boundary of a 4-manifold. We could take S2 to be the boundary of a ball times time. So that could be our 4-manifold. And then the data in the 4-manifold at time 0 would be a ball with on its boundary the n points. It makes a lot of sense that by studying that, you'd see the Jones representations at non-integer k. I can't say that I've tried to think it through properly, however.
Thank you. So I guess I don't see any more questions. So I guess we can all virtually thank the speaker, Ed Witten, for his marvelous talk. Thank you very much, Ed.
Thank you.
Yeah, thank you very much. Yeah, that's a great talk.
Thank you. Great seeing you all. Good luck to everybody. And I know that it's safer in Beijing, but anyway, everybody stay safe.
But
Bye-bye.